Welcome. This is the second session on dual spaces, part of linear algebra. So I would like to review what we did in the first video, namely about linear functions on n cross n matrices. Okay. For about 5 minutes I did not share the screen, but I went through it a little fast when I realized that. So I would like to do that again in a slightly different way also. Okay, so let us get started. So let us recall we had M and R, which is all a n cross n matrices with the real entries. What I am doing is also true for anything. Okay, then we identified M and R with Rn squared via if A is something like A11, A1n, AN1, ANN, then this goes to A11, A1n, A21, A2n, dot AN1, ANN. Right? So this isomorphism is a linear isomorphism. This is a bijection, it's a linear isomorphism. This is all known to all of you. Right? And therefore we know, okay, any linear map, any linear functional f from M and R to R is of the form f of A equal to summation alpha ij aij, summation over j and I equal to 1 to n, 1 to n. And what are alpha ij? Alpha ij are some f of aij, where aij is the standard basis of M and R. What is aij? Its RS entry is 1 if RS equal to ij, the ordered pair equal to this, otherwise 0. That means ith row and jth column 1, rest are all 0. Okay, then I can write any A as summation aij if this is of the form aij eij. So if I write only one summation, understand it's summation over I and j. Okay, right? Is that clear? So we know that therefore f of A will be summation f of aij eij, f of this, and by additivity it is going to be f of aij eij, and by linearity this is going to be aij summation and f of eij. So if I denote by alpha ij, then I got it. Okay, so this is very easy. But what we need, an intrinsic description. What do I mean by intrinsic description? See, these are the things which are a little more advanced, but usually teachers avoid at BSc level, but I would like to say what it is. See, what I mean by intrinsic is when I look at M and R, this set of matrices, okay, we have a linear isomorphism of M and R with Rn squared. By choosing a basis, then we are able to show that. Okay, but what I would like to say intrinsic is something to do with the set of matrices. That is, in terms of matrices, I would like to express the linear map. Okay, for example, suppose I take nth degree polynomial, vector space of all polynomials of degree less than or equal to n. I know it's n plus 1 dimensional space, but if just because it's a polynomial, I have the natural linear map like differential operator d by dx, right? They give me a polynomial px, then I know p dash of x. Whereas if I try to define in terms of coordinates, it will look very strange. Something like a0, a1, a2, etc. Then a0 it is mapped to 0, a1 is mapped to a1, and a2 is mapped to 2a2, 2a1, etc. Okay, are you following? So we would like to make it somewhat more intrinsic. Okay, don't worry, we are going to explain what this is. Wait a minute. So let us define bji to be f of eij. Okay, then I have a matrix bj, sorry, bji 1 less than or equal to ji less than or equal to n, right? Then let us look at what this is. Therefore f of a from whatever I return is a ij and b j I, okay, j equal to 1 to n, I equal to 1 to n, right? I can also write it the other way around, but let's not worry about it. I can also write it as b j a I j, then I will sum it over I n j. They are the same. But do you realize what this is? If C is the matrix AB, what is ith entry? Ith entry is given by Aij Bji summation over j. You understand this? Therefore, this is nothing other than summation Cii. But that is nothing other than the trace of the matrix B, trace of the matrix C. Therefore, what I have is, okay, I have that f of A is nothing other than trace of B A, where B I j, where B equal to Bij and Bji is f of Eij. Do you understand this? Now let's stop. Okay, pause, review, proceed. Or maybe even before that, let's try to understand what this means. In what way it is intrinsic? Remember, if f is a linear functional, I have found a matrix B in MNR, and then A going to B times A, that is a linear map. Okay, from where to where? Okay, anyway, it's a matrix operation, right? This is a matrix product, and trace of a square matrix is also well defined. So you can see this description is somewhat intrinsic. Okay, so what we have proved, if f from M and R to R is linear, then there exists a matrix B in M and R such that f of A is trace of BA. Okay, you understand this? Okay, now is the converse true? That is, fix converse. Let B be in M and R. Define fb of A by definition trace of BA. Then fb from M and R to R is linear. Okay, why? Because remember, from M and R one can directly prove, okay, let us directly prove f of B plus A1 plus A2 is trace of B into A1 plus A2, but this is nothing other than trace of BA1 plus BA2, because matrix multiplication is distributive, but trace is additive. Therefore trace is of BA1 plus trace of BA2, but that is FB of A1 plus FB of A2. Therefore this is additive, and similarly FB of C times A is C times FB of A. Okay. Right. Okay. But let us try to make it slightly little more because I want my viewers not only to learn mathematics in the modern way, so that they should improve their standard. Okay, so let us look at this. This is multiplication by B, A going to A times B, and from there T going to trace, or trace of T. Okay, this is a linear map. From where to where? From the vector space M1R to the vector space M1R, and this trace map from T M1R to R is a linear map. Therefore my FB is a composite. Call is mu times B, multiplication by B. Therefore this is composite of trace composite mu B. Right? And these are linear maps, therefore composite is a linear map. Right? So what you have proved is the following theorem. Yeah, from MNR to R is linear if and only if there exists a B in MNR such that F of A is trace of AB or trace of BA. It doesn't matter. Okay. Pause. Review. Proceed. Okay, this is what we did toward the end of the thing, and I am essentially repeating for two reasons, because it's worth knowing, and second thing, whatever I have done can be done for any matrix space of the kind M cross N. Okay, set of all matrices M cross N to R, the same kind of thing. Okay, I shall leave that as an exercise, number one. Number two, as I said, I always try to connect with various things, because that is the way you can get mastery over the subject. So it should not be very narrow minded. So what do you plan to do is, I hope some of you had already learned inner product spaces, finite dimensional inner product spaces over R. Okay, from my earlier videos on inner product spaces, I want to make use of that. Okay, so that way you will get a much better perspective. Why? How did I know I should be able to write F of B, F of A as trace of A times B? How do I know that? How did I expect that? I just did some manipulation. All of a sudden, why did you think of a matrix? Okay, these are the kind of thing one should be intrigued. One should find out, is there any reason behind that? We are going to unravel it. So let us look at B is a finite dimensional inner product space over R. Okay, then we have what is called a Riesz representation theorem. What is that? If F from B to R is a linear functional, then there is a unique V in V such that for all x in V, F of x is inner product xv, where inner product is okay. Yeah. Now let us look at M and R. Okay. So I have an inner product on that. The inner product is, give me x and y. Okay, that is M and R cross M and R to R. The mapping is xy going to trace of y star x, where y star is the transpose of y. So this is an inner product. Okay, If you had watched my videos on inner product space, you know that, otherwise you have to check it. The crucial thing is positive definiteness, but then positive definiteness is, this will be y star y will be x star x, that will be positive definite matrix unless it is 0. Okay. Okay. Yeah. Or watch the relevant video of mine. Right. Therefore, if I have a linear map f from M and R, I can think of it such as this is a linear map from this inner product to R. Right. Therefore, there is a unique B in M and R such that f of A is trace of B star of A. Let us say unique T such that unique T star of A. Trace star of A. Therefore, my T star is B or T is B star, as where B is as earlier. So I know there must be a matrix B, so I wanted to write down the matrix. Okay. All review, proceed. Now is the mystery solved? You see that? One can line by line check the proofs, but one should always understand how anybody thought of that. Is there any reason? That kind of questions are always meaningful. Okay, that's what we are trying to do. Okay, right. Now let's go back. So as I said, the whole thing can be generalized to matrices of the kind M cross N R. Okay, this is R to the power Mn. The same way, then you can again see if you piece a linear map from M cross N to R, then there is a B. Can you guess where it should be? It will be M, N cross M R, so that f of A is trace of BA. Now B will be N cross M and this will be M cross N, therefore this will be N cross N matrix. Do you understand? How do I do that? It's the same, exactly the same way for each I, 1 less than or equal to I less than or equal to M and 1 less than or equal to J less than or equal to N, I define B, J I to be f of Eij like earlier. What is Eij? Again the same matrices. Okay, basis, standard basis of M cross N of R. Right? Therefore, J where is over? Therefore, I get a matrix B which is Bji, but J runs from 1 to N and I runs from 1 to M. Therefore, this matrix belongs to M of N cross M R. Okay. So, I leave the details. Okay. Please check. Okay. Again, the reason I say on M cross N R. Okay, I have an inner product. Okay, xy is going to be trace of y star x. So that is why we can again expect. Okay. Okay. Now we want to digress into next one. Okay. Let us look at polynomials. Again, let us stick to only over R. This is the next example. Okay. Now we have a natural basis 1 x power n. Okay. So I can ask what is the dual basis. This is going to be something very interesting, right? So let us again, so call this as polynomial. Let us call this Pn. Then I want F is in Pn star. Let me call it at phi. Okay, phi is in Pn star. This is a dual of Pn. Okay, I want to understand the dual basis. How do I do that? Let us look at my, therefore phi I, the dual basis. Okay, suppose this is a dual basis. Let me write 0 less than or equal to I less than or equal to n. Okay, this is a dual basis. Okay, this is your E0, E1, En. If you want to think of it that way, that is phi I of x power j is delta ij. Right? Now, if this is the case, let us look at what happens to a polynomial. Suppose my p of x is something like a0 plus a1 of x plus an of x power n. Then if I operate phi I on x, what is going to survive? Only the term on this will survive, therefore I get a. Do you understand that? Yeah? Phi I of a0 will be 0, phi I of a1x will be 0, because that will be a1 times phi I of x. Then I will come to ai, phi I of x power I, that will be 1, the rest are all 0, right? Okay? So this is the dual basis. But remember, again I want an intrinsic. What do I mean by that? Now let's look at if my polynomial p of x is a0 a1x plus ai x power I plus dot dot an x power n. Notice that this ai is nothing other than the polynomial to the power, take the ith derivative, right, at 0. Then what will I have? If I keep on differentiating, I will have I minus 1 into 2 into 1. Then I would have differentiated any time. Then I will have into a. You are following? Therefore, I will have a is going to be this divided by I factorial. Do you understand this? Hence, my phi I of p is nothing other than p ith derivative at 0 divided by I factorial. 0 less than or equal to I less than or equal to n. Now this is the intrinsic. Give me a polynomial. Okay. Very nice. Of course, getting at a is also intrinsic, because once you give the polynomial, the coefficient is given to you. But this says another way. Okay. So this is the thing. Is that clear? Okay. Oh, P R P. So before we go further, let us look at something a little more general. Suppose I take P to be all polynomials. That is all real polynomials of all possible degrees. Then you know it is infinite dimensional. Right? Okay. Then this P, I can identify this a n with n over z plus, so that there exists n, so that for all k greater than or equal to n, ak is 0. Remember, it's a polynomial, therefore any polynomial p will be some a0 plus a1x plus an x power n, right? I can think of it as 0 times x power n plus 1 plus or so on. Therefore, for each polynomial I can associate an infinite tuple an, after that is 0 0 0. Do you understand that? Okay. If you don't like, let us look at, let C00 equal to all sequences an, so that they are all null sequences. Okay. And eventually 0. Of course, there will be not automatic null sequence. What do you mean by eventually 0? That is given a here. A is of the form an. For this a, there is a natural number na, so that for all k greater than or equal to na, ak is 0. Right? The picture is as I drew earlier. Let me assume this sequence is n from z plus. So a naught, a1, ana, after that 0, 0, 0, 0. Okay, this is the vector space. Okay, with the addition will be an, bn will be n plus bn, etc. And lambda times c times an will be c times an. Notice that this again belongs to CW0. You have to check this. That's very obvious. If n1 is for A, n2 is for B, then certainly I know n1 plus n2. If I take or maximum n1 n2, then after that stage an plus bn will all be 0. Yeah. Okay. Now suppose f is a linear. Notice that there is a basis for this. Basis for CW0 is en, where en is 0, 0, 1 at the nth place, and 0 before, and 0 after, and 0 everywhere after that. That is en if the kth element is 1 if k equal to n, or 0 otherwise. Think of this as a sequence. Kth term is 1 if k equal to n, otherwise 0. Right? Therefore, any a can be written as a1 e1 plus an, if you want en where I write n equal to na. Okay, after that 0, 0, so I can omit that. You understand this? Anything is a finite linear combination of this thing, and it's unique. Therefore, that's a basis. Right? Now, let us look at if f is a linear map from CW0 to R, then this f of a will be, as in this notation, it will be f of e1 plus f an f of en, e capital N. You understand that? But this, notice that depending upon a, this n will also vary. Think of this, if you want to think of this as a polynomial, f of p of x will be a naught f of e1, which is 1, plus a1 f of x plus a2 f of x squared, and plus an f of x power n. Okay, pause, review, proceed. Therefore, what we find is, given for every f in p star, the dual, there exists a sequence bn, okay, so that, okay, is a real sequence, so that f of a is summation ak bk, k running from 0 to infinity. But notice that since a belongs to p, okay, this sum is finite. Yeah. Therefore, there is no, the important thing to observe is, key observation, while a belongs to CW0, okay, is eventually 0 sequence, b is any sequence. B is any sequence of real numbers. No conditions. What do I mean by that? Take b equal to bn, no condition. Then I define fb from CW0 to R by fb of a equal to summation ak bk k equal to 0 to infinity. But this is always a finite sum because a belongs to this. You follow that? Now you can see something interesting. Okay, and any, Okay, therefore what do I have found? P star dual is all sequences. Now what is the dimension of P? If you know that this is countable, sorry, it is C. Okay, this is countable, sorry, because P is union of Pn, but dimension of Pn is equal to n plus 1. Okay, therefore this will be countable dimension, countably infinite dimension. But P star is all sequences, all real sequences, vector space of all real sequences. Therefore dimension of P star is at least C. Okay, it is actually C to the power. This is, see here, anything b naught I can put n is r, anything, therefore it's r cross r cross r, that is r. Okay, over infinite. If you know Cartesian product, this has cardinalities. Okay, cardinality of r. Okay, this actual dimension of P star is cardinality of r, but let's not worry about. So the crucial thing you should know is in infinite dimensional case, dimension of V need not be equal to dimension of V star. Okay, pause, review, proceed. If you are a BSc student, please go through it, revise that once more. Okay, that will be a very interesting thing. Okay, don't worry about cardinality, etc. But you can see the P star looks somewhat very big. Okay, that impression is good enough, but because you are able to identify in infinite dimensional space also all kinds of things. Okay, that is more important. Yeah. Okay, let's go to the next thing. Now let's look at very general case. Suppose I have set X. X is a set. Okay, let us look at all functions from X to R. We know this is a vector space. Okay, if X is infinite, then Fx R will be infinite dimension. Okay, if you had watched my first set of videos on vector spaces in linear algebra, you know all these things. But infinite dimension I may not have proved, but anyway, that's very easy. But it's not going to be important thing. Now I want to find linear mass from f of x r to r, linear. Okay, now how do I define this vector space? Just to be on safer side, let me do that is define f plus g, that must be a map from x to r. Therefore I define f plus g at x. I have to tell you what it is, but I know what is fx, I know what is gx, they are real numbers, therefore I add them. Therefore f plus g's value at x is there, is fx plus gx. Therefore I have defined f plus g vector addition on functions. Similarly, scalar multiplication cf at x will be c times fx. So with respect to this becomes a vector space. Okay, now think about it. What does it mean? Give me any function f from x to r, phi of f should be a real number. Given any function, real valued function on x, I want a real number out of that. What is the very natural way of getting it? See, this is a creation. Okay, I can just say that and you can verify. Think about it. Okay, see here also I said f plus g at x must be a real number. How do I get it? I know fx is a real number, gx is a real number, therefore I added. So now what will I do? So the idea is fix. Okay, f p, or let's say a in x or x naught in x, then define this to be f of a. Okay, now f of a is a real number and it's linear because phi of f plus g by definition is f plus g at a, but that is according to our definition, it is f at a plus g at a, therefore it is phi of f plus phi of g. And similarly phi of cf, that is equal to cf at a, but cf at a by definition c times fa, but that is c times phi of f. Okay, therefore, okay, for we have produced a lot of linear functionals, namely call that phi of a. Let me call phi as phi of a. So phi of a is f at a, phi of x as x square is capital X. We are not claiming these are the only ones. Okay, for example, since these are linear functions, then for x and y in capital X, I can define phi x plus phi y. At that f will be phi x of f plus phi y of f, that is fx plus fy. That will also be linear functional. It may not be of the form phi z for some z. It need not be equal to phi of z for some z. You understand? Okay. Keep this in mind. Okay. And we put extra condition. Suppose I look at all continuous function on 0, 1. So my x is 0, 1 and this is part of all functions from the space 0, 1 to r. That is f of x r. Okay. Therefore, I have defined a linear function f going to, let us say, f at some a, where a is in 0, 1. In particular, a could be 0 or a could be 1. It's a natural choice. But remember, I also have another linear function, that is, give me an f, set it to 0 to 1 f of x dx. Since f is continuous function, therefore this is a linear map, we know that, and this is a real number, the integral exists, which is a real number, and this is linear. Okay, it need not be of the form, right, phi of x. Okay, is that clear? So pause, review, proceed. Now let's come back to polynomials again. Do you find it tough to cope with? At each PRP, stop, review. Okay, try to understand. And it will be nice if you have a friend with you, you can discuss with him or her. That will make your life much easier. Okay, now let us these are all polynomials are real polynomial overall. That is real polynomial, right? Therefore, give me any polynomial p, okay, in Pn, then I can associate it to something p of x. Okay, p going to p of x, where fix a real number x in R. Right? Think of this as a function, and therefore evaluating. Okay, I will write for any polynomial in terms of capital X. That is a0 plus a1 capital X plus an capital X power n. Therefore, this x is a real number. Small x is a real number. If you want, think of it as alpha or a or some such thing, if that confuses you. Okay, so this is the value of the polynomial function at x. Okay, so we know these are all linear. Call this phi of x from Pn to R. Phi of x at the polynomial p is the value of p at x. So this is linear, right? Now, so I have produced lot of linear things. Remember, Pn is a finite dimensional, therefore Pn star we know is also finite dimensional. The dimension is actually n plus 1, which is the dimension of Pn, right? So natural question I can ask, if suppose you give me point x0 to xk, okay, distinct points, how many points? K plus 1 point, okay, when they are linear, when this pi x, let me write phi I equal to pi of xi 0 less than or equal to I less than or equal to k, right, when phi I are linearly independent. Is the question clear? Pause, review, proceed. Okay, now let us try to understand. Okay, notice that since we know Pn star has at most n plus 1 dimension, therefore obvious guess will be k must be less than or equal to n, because this will be n plus 1 elements, right? K plus 1 elements, k plus 1 should be less than or equal to n plus 1, that means k is less than or equal to n. Do you understand this? Yeah. So I want to prove that. So what do I mean? Okay, so assume k is less than or equal to 1, and to prove phi I 0 less than or equal to I less than or equal to n is linearly independent set. Right? So how do I prove that? Let's assume C0, phi 0, C1, phi 1 plus Ck, phi k equal to 0 as a linear functional. Okay, this is where this belongs to P star. This is also a vector in P star. Right? So if that is 0, what do I want to prove? I want to prove whether for all I Ci is 0. If I want to prove this is linear independent, I have to do that. So what is the trick? The trick is that is I want to operate, call this as phi, I want to operate phi on a polynomial p, okay, right, and I should get, suppose, okay, for each I choose a polynomial pi, so that if I operate phi on pi I get Ci. Okay, but this is 0, that means Ci will be 0. Do you understand this? What do I mean? I want to prove each Ci is 0. Therefore, let us assume for each I there exists a polynomial pi, so that phi at pi gives me Ci. Okay, then I will be through. Because when I operate on pi, what will I get? I will get this as Ci. Therefore, but phi of pi is identically 0, therefore phi of pi is 0, therefore Ci is 0, and this is true for all I, therefore linear independence follows. Is the proof clear? Idea, not proof, idea. Okay. So this is where the so-called Lagrange interpolation idea comes into play. So fix, okay, x0 xk, okay, all distinct. Define Li of capital X to be product j not equal to I of x minus xj. Remember, capital X is this is the indeterminate. If you don't like, call it aj divided by j not equal to I of xi minus xj. Okay, these are all distinct, therefore the denominator makes sense. This is not equal to 0. This makes sense, right? Therefore this is a constant. So this is a constant. Okay, therefore it is same as some constant times product j not equal to I of x minus xj. And where does j run from? J runs from 0 to k. That is k plus 1 element, but one element is missing. Therefore this is exactly polynomial of degree n, k, right? Therefore k by assumption is less than or equal to n. Therefore this polynomial belongs to Pn. Do you understand this? Pause, review, proceed. What is the beauty of this polynomial? The significance is Li x is a polynomial, right? This is a polynomial. Therefore let me look at Li at xj. Okay, for 0 less than or equal to j less than or equal to k, let us assume j is not equal to I. Then you can see the product I have is xj minus, let me write Li at xr r not equal to I. So xr minus xj, j is not equal to I by product. This constant, let me call it some constant. This constant, let me call it Ci. Okay, because that's not going to matter at present. Okay, Ci times, okay, later this by product xi minus xj, j not equal to I, right? So Li of xr is product j not equal to I of xr minus xj. At place of x I have to substitute xr, and this is divided by xi minus xj, j not equal to I, right? Therefore since r is not equal to I, that there will be this r will belong to this, therefore this numerator is 0, therefore this is equal to 0. But on the other hand, Li at xi, you can see this is product of xi minus xj, j not equal to I, divided by the same object, therefore it's equal to 1. Okay, therefore Li has the property Li at xr equal to delta IR. That means equal to 1 if r equal to I, sorry, yeah, is 0 if r is not equal to I. Okay, pause, review, proceed. Okay, now let's come back to the, so I have Li with this property. Now let's look at, let's go back to this. What did I assume? My phi is C naught L naught plus Ck Lk is identically 0. These are all, this is taking place in Pn star, right? Therefore if I look at phi, its action on Ck Lk 0 less than equal to k less than, oh Cr, sorry, Cr Lr 0 less than equal to r less than equal to k, then this is going to be, I want to know what this is. Sorry, I'm again sorry. I got, that's why I should have gone back. My phi is C naught phi naught plus C1 phi 1 plus Ck phi k, where phi j at, okay, phi j of any polynomial is p at xj. Recall that? Recall the way we define phi j, right? Therefore this is equal to 0. And where is this equation valid? In V star. Now let me operate this on Cr Lr. Okay, this must be 0. Simply operate on Lr. Okay, Lr, right? This is C naught of phi naught of Lr plus C1 phi 1 of Lr plus Cr phi r of Lr plus Ck phi k of LR. Do you understand this? Because this is linear. But remember, this is C naught of, what is phi naught of LR? That is LR at x0. Next one is LR at x1. And here it will be CR times LR of XR. The last one will be CK times LR at XK. But what do I know? These are all 0. This is 1. This is 0. Therefore, I get CR equal to 0. For which R? Okay. Therefore, I have shown this. Okay. If X, what have we shown? Let me complete. Stop this lecture after summarizing in summary. Okay. Fix x0 xk distinct real numbers and k less than or equal to n. Define phi I of any polynomial p to be p at xi, where p is a polynomial in Pn. Then phi 0, phi 1, phi k is linearly independent. In particular, this is a basis Pn, because how many elements are there? N plus 1 elements, and this is linearly independent, and dimension of Pn is n plus 1. Therefore, this must be a basis. The question is, can we identify the dual basis? Right? In Pn, polynomials of degree less than or equal to n, it's an n plus 1 dimensional vector space. There is a standard basis 1x x power n. And what have we done? We generated a lot more linear functionals. What are they? They are evaluation function. That is, fix any real number a, then map the polynomial p to p of a, evaluate p at a. Okay, then we saw it's a linear function. Therefore, if I start with a1, a0, a1, a2, ak, where k is less than or equal to n, distinct points, that is k plus 1 distinct point, then I have corresponding linear functions phi naught, phi 1, phi k. So phi, okay, that is phi j at the polynomial p is p at xg, p at ag. So we showed that these are linearly independent, and hence we found it's a basis. Right? Basis of what? Pn. Natural question is, can I identify the dual basis in a very concrete way? We will do it in the next lecture. Are you happy? Okay. Are you getting comfortable with the dual space and dual basis, etc.? Review all of them. You will see it's much easier. Okay. Stay tuned. We will be back. Take care. Stay safe.